Hello everyone. In this video we are going to talk about AVL trees. In the previous video we have talked about the binary search tree. In fact, AVL tree is going to be an extension, a specific version of a binary search tree that we put some restriction to make sure that we get a balanced height. So I'm going to define the height of the balancing height actually, and then we will see that how we can modify our implementation for binary search tree to make sure that the height is balanced and we always get the best possible height for our tree, which was theta of log of n if you have n nodes in your tree. So remember in the previous video when we discussed about binary search tree, we defined binary search tree to be a tree that contains some values which are comparable. We can order them in some order, a specific manner, and always for all the nodes, the left subtree, every node in the left subtree is going to be smaller than the value at the root, and everything on the right subtree are going to be greater than the value in the root. Okay, so this definition doesn't really put any constraint on the shape of the tree or the height of the tree. So if you have a set of items, depending on how you are inserting them in a binary search tree, you may end up to a tree like this one, that you can see that the height of this tree, depending on the number of node, is going to be log of n. Or you can actually end up to a tree like this one, that the height of the tree, depending on the number of nodes, is going to be theta of n, or in fact the height here is going to be n minus 1. So this is an issue, because if you get a tree like this one, this is not really a tree anymore. Although the data structure that you are using is a tree, but in practice, this is going to be like a list. This is a linked list. So if you are searching for an item, if you are inserting a new item, if you are removing an item, the cost is going to be depending on the height, which is going to be n, and this is bad. Unlike that, if you get a tree like this, which is balanced, in fact, this is a perfect binary tree. We don't always get something like this, but if we get a tree similar to this with the height depending on log of n, the time complexity of insertion, remove, or searching an item, all of them are going to be depending on the height, which is going to be log of n. So this is our issue with binary search tree, and we are going to fix that using the some definition for the what we define a tree to be a balanced tree, and how we can force our binary search tree to be a balanced tree. So before we actually go to the definition of the balancing, I'm going to, the formal definition, I'm going to show you some example. Think about having 3 items. Let's just call them 1, 2, 3. All of them are, comparable to each other. And you can define an order between these integer numbers, right? And I'm going to create a binary search tree using these 3 values. Depending on how you actually insert these items, in which order you insert them in an initially empty binary search tree, you will end up to one of these 5 different binary search tree here. In total, if I have 3 items, 3 different items, the total number of permutation is going to be 3 factorial, which is going to be 6 different ways. But if I insert the items in the order of 2, then 1, then 3, or 2, then 3, then 1, both of these 2 are going to end up a tree like this. So that's why I only have 5 different possible binary search tree using 3 items. Now let's look at these different shapes. If you think about all of these shapes, only the middle one is the one which we call it actually balance. In all the other cases, you have the worst height, right? The shape of the tree is in fact look like a list, not a tree. All of these cases are more like a list. They are not good. The best thing that I'm looking for is this one. And so I will define the balance to be a tree like this, and all of the other cases are going to be imbalance. I am going to fix them and get, if I get any of these shapes, I'm going to change it and make sure that I will get a tree like the middle one. Before I give you some way to fix it, I'm going to also look at these 4 different imbalance in more detail, because they are going to give me the main 2 patterns that we will fix, and these patterns are going to be the main patterns that we need to fix in any binary search tree. I will show it to you later. But let's have a more deep look at these 4 different patterns. If you look at the pattern A and pattern E, you will see that they are quite similar to each other. This one is imbalanced because it's actually going right, and this one is imbalanced because the tree grows left. We are calling this left or right imbalance, and basically these 2 patterns are exactly the same. Whatever I do for fixing A can be applied to fix E as well, just the reverse of that. Whatever I do on the left side, if I do it on the right side, is going to be whatever I do on the right side of A, if I do it on the left side of E, I can fix the imbalance. So these 2 patterns are actually one pattern that I'm going to discuss. The other thing is that if you look at B or D, both of these are going to, in fact, have the similar shape. This one is imbalanced in the form of right-left, and this one is left-right. We call it right-left or left-right imbalance. So whatever I do to fix the pattern B, I can apply it to fix the pattern D, just the reverse of that. So basically, at the end, we are going to have 2 main patterns that we are going to focus. I'm going to actually focus on A and B. If you just reverse whatever you do, you will get the answer for D and E. So now let's look at these 2 specific prototypical cases. Assume that I have a tree like this one. This is a binary search tree, right? And this is balanced. I can't do anything better than this using these 2 items. Whatever I do, this is going to be the shape of the tree. But then if I insert 1, you can see that 1 will be inserted to the left of 2, right? But this tree is not balanced anymore. I have an issue. I have to fix it. I want this tree to have the minimum height that I can. So if you look at these, so I'm going to actually change this tree to be in this shape. But if I think about the values that I have here, it tells me that the middle value should go to the root. What is the middle value? The middle value is here. If I actually have a look at this pattern that I have it growing in left, the middle node should be the root node. So I need the tree to be in this shape. To make sure to actually convert this tree to this tree, the left one to the right one, basically I just need to rotate around the left child. Okay? So this is exactly what I need to do. From the root node that you find it imbalance, in fact, if I rotate around the left child, it is going to give me the balanced form. This is exactly the same thing that you need to do for the tree in this form. If you rotate around, in this case, if you rotate around the right child, you will fix it and it will be balanced if you rotate around the right child. and the result is going to be balanced. The other case is this one, that just assume that you have 3 and 1 in your tree. This is a balanced binary search. You can't do anything else using 2 nodes, and then all of a sudden 2 will be inserted. So 2 is smaller than 3, and so it goes to the left, but greater than 1, so it goes to the right, and then it will be inserted here. Again, this is not balanced. This is more like a list than a tree. I wanted to change it to be in this shape. So if you have a pattern like this, unlike the previous case, the middle node is not 1. The middle node is in fact in the leaf. So I need to take this one and make it to be the new root. So the pattern of fixing here is different, right? In fact, the leaf node needs to actually go up and become the root, and 3 actually, the previous root value became a child of 2. Okay, this, you can see that this pattern is completely different than the previous pattern. So these are the main 2 patterns that we are going to discuss. This is a very simple case of that. I will show you the more general case of these patterns. So now I can actually define what is AVL tree and what is AVL balanced. But before discussing that, I'm going to just recall that the height of an empty binary tree, or any actually tree, is going to be -1. This is the definition that we had and we always had for that. And the height of a tree which only has 1 node is going to be 0, right? Just keep this in mind, and then I'm going to give you the formal definition of AVL balance. We will say that a binary search tree is AVL balanced if the difference between the height of the left subtree and right subtree for all the nodes are going to be at most 1. If I'm going to give you a recursive definition, this is going to be the difference between the height of the left and right subtree of the root node is at most 1, and both the left and right subtree, both of them are AVL balanced as well. So basically you are just applying this constraint over all the nodes. The name actually comes after the name of 3 scientists that they find some specific, very interesting theorem about this balancing, this definition, this AVL balancing. And that interesting theorem is that we can prove that the worst case of the height for the AVL tree with n nodes is theta of log of n. What does this mean? It means that if you make sure that your binary search tree is AVL balanced, or we can simply just call it, if you have an AVL tree with n nodes, the height of your tree is going to be in theta of log of n. And this is exactly what we are looking for, right? If we can make sure that our tree or binary search tree is AVL balanced, we get the best time complexity for the height and for all of the methods, like for the insertion, deletion, and the searching in the binary search tree. So let me show you a couple of examples of AVL trees. If I have just 1 node, so 1 node is going to be AVL balanced. 1 node is a binary search tree and it is AVL balanced, right? Because if you think about it, the left subtree, the height of left subtree is -1, because basically the left subtree is null, right? It is an empty tree. So the height here is -1, and the height of the right subtree is also -1. The difference between them is 0. This is exactly the definition of AVL balanced. If I have 2 nodes, either in this shape or in this shape, okay, this is going to be AVL balanced. And the reason is that the height of the left subtree is -1. This is an empty tree. And the height of the right subtree is 0. If you only have 1 node, the height of that is going to be 0, right? The difference between -1 and 0 is 1. So this is AVL balanced. And this node is also AVL balanced as well, right? This is AVL balanced. And similar to that, we can discuss that this is AVL balanced as well. If you have 3 nodes, the only shape which is giving you the AVL balanced is this one. And the reason is that the height of this, this is AVL balanced, this is AVL balanced. The height of left subtree here is 0. The height of right subtree here is 0. The difference is 0. So this is AVL balanced as well. If I have 3 nodes, I cannot give a tree like this one. This is not AVL balanced. This is not AVL balanced. And the reason is that the height of this subtree, this one has height 0, this one has height 1. So this is AVL. This is AVL balanced, but this one is not AVL balanced. And the reason is that the right subtree is -1 the height, and the height here is 1, right? The difference between these two is going to be 2. So this is not AVL balanced. So if you have a tree like this, this is not going to be AVL balanced using 3 nodes. This is exactly one of the patterns that we have discussed before, right? And you can similarly discuss that if you have 3 nodes, a tree like this one is not going to be AVL balanced. This is not AVL. And the reason is that this is not balanced. This is balanced, but not this one. This is not going to be balanced. If I have 4 nodes, I can create an AVL tree like this one. This is AVL balanced, and the reason is that this is AVL, right? If you have just 1 node, this is AVL. This is AVL as well, because the left subtree, the height is 0, the right subtree is -1, the difference is at most 1. This is AVL. And this one is AVL as well. This one is also AVL. Why? Because the height of the left subtree is 1, the height of the right subtree is 0, the difference is 1, right? So this is AVL balanced. Not only this one, if you have 4 nodes, you can have a tree like this one, or you can have a tree like this one, or you can have a tree like this one. So you can see that this constraint, this AVL balance constraint, gives you a lot of freedom. If you have 4 nodes, it's not necessarily going to be in this shape. It can be in this shape, it can be in this shape, or it can be in this shape. All of these are going to be AVL balanced, okay? But you cannot have a tree in this shape. You can see that this is not going to be AVL anymore, because this one is not AVL and this one is not AVL as well. Okay, let me show you a larger tree. Using 42 nodes, I can create a lot of different AVL trees. All of them are binary search trees, and all of them are AVL balanced. You can see that although this tree is not very similar to a complete binary tree or a perfect binary tree, but still this is AVL balanced. If you look at all the nodes, they are balanced, they are AVL balanced. The difference between the height of left subtree and right subtree is at most 1. For example, if I give you some example like this, that for this node, this is AVL balanced. Why? The root node is AVL balanced. The reason is that the left subtree, the height of left subtree is 4, the height of right subtree is 4. This is AVL balanced as well. Why? Because the height of the left subtree is 2, the height of the right subtree is 3. The difference is exactly 1, so it's not more than 1. This is AVL balanced. This is AVL balanced as well. The height of the left subtree is 1, the height of the right subtree is 0. The difference is 1. This is AVL balanced. The height of the left subtree is 2, the height of the right subtree is also 2. The difference is 0. If you look at all of these nodes, they are AVL balanced. The height of the left subtree for this case is 1, the right subtree is 2, the difference is at most 1. This is the case for all the nodes. This one is AVL balanced. The height of the left subtree is 1, the right subtree is 1. The difference is 0. You can see that you can check the difference between the height of left and right subtree for all the nodes, and you will see that this is an AVL balanced. So no, we know about this theorem. I don't want to actually prove the theorem. The math is beyond the scope of this course. So just take the theorem from me that if you have a tree in the shape of, which is AVL tree, which is AVL balanced, we can prove that the time complexity will, based on the n, is going to be theta of log of n. This is exactly the best thing that we are looking for. So now the remaining of our discussion is that how we can maintain a AVL balance in our binary search tree. It means that I'm creating a binary search tree, right? By adding a new node, you are inserting an item, removing an item, searching for the item, which methods needs to be updated to make sure that I will always keep my binary search tree to be an AVL node. One thing that we can figure out here is that among the three main methods for the binary search tree, only insertion and deletion needs to be updated. If you're searching for an item in a binary search tree, you are not changing the shape, right? So, but if you are inserting a new item or if you are removing an item, you are changing the height of the tree. It is possible that you change the height of some of the nodes in the tree or the whole tree. And because of that, it is possible that you make it imbalanced. So at first we assume that, okay, the initial tree, which is a binary search tree, the initial tree, which is an empty binary search tree, this is AVL, right? You insert an item, just make sure that after you are inserting an item, still the tree is AVL. If you are removing an item, still the tree is AVL. So I'm going to just look at the implementation that we had for insertion and deletion in binary search tree and modify them to make sure that after inserting an item or after removing an item, the tree is still AVL. So let's look at some example. Think about this tree. This is an AVL tree, right? All of the nodes are AVL balanced. The difference between the height of left subtree and right subtree is at most 1. Then I will, for example, insert something like 15 into the tree. Where it will end up, just this is, the first phase of the insertion is exactly what we do in the binary search tree. Just find the correct position for the node and insert it there. 15 is less than the root, you go to the left. It is greater than 12, you go to the right. It is smaller than 17, you go to the left. And then you will see an empty tree or a null reference. So you will create a node, put the item there, and just maintain this reference for the parent for the 17. So 15 will be inserted, right? Now after I'm done with inserting the node, I need to check if inserting 15 will cause any imbalance or no. What I need to do is that just checking all of those nodes that has been visited, starting from the root to insert this node. You will see that when I was inserting 15, I saw root, then I go here, then I go here, right? And then I actually went here and inserted 15. So the only nodes that can be affected are these nodes, starting from the root until you actually inserted that node. I just need to check the height of these nodes. I don't need to be worried about 44 here, any of the other nodes. The only nodes that I need to be worried are in this path. These are exactly the nodes that we had the function call over them. So it makes it really simple when we are writing a recursive definition for insertion. You just need to check after you are done with the insertion, just check that if you have updated the height or not. If you have updated the height, you have to make sure that if you are imbalanced or no. So if I look at this specific example, we will see that the height of 17 hasn't been changed. The height of 12 hasn't been changed. And the height of 36 hasn't been changed as well. So basically, I don't need to do anything in this case. the tree, and if you think about the tree is still AVL balanced. None of these, the height of none of these nodes has been updated, and all of the nodes are going to be balanced. Therefore, all of the nodes are going to be balanced. I don't need to do anything. So you will see that after the insertion, in some cases, I don't do anything. But in some cases, you might cause an imbalance and you have to fix it. Let me give you another example. Just assume that we are inserting something like 42. If I insert 42 in this tree, this is greater than the root, right? So you go to the right. It is smaller than 44. You go to the left. It is greater than 38. You go to the right. There was nothing. You create a node and you put the 42 here. So now which nodes has been affected? Again, all the nodes starting from the root until you end up to that specific position that you insert the item has been affected. Right? I mean, there is a chance that they can be affected. Now, let's see that. Are they really affected? Did we change the height of them or no? The height of 38 has been changed. It's from 0, you changed it to 1. And the height of 44 has been changed as well. From the height 1, it has been changed to height 2. But does it change the height for 36? No, the height of 36 is still 3. And we didn't actually change the height there. 3 to 3, so there is no difference here. The two nodes that has been updated are these two. I need to also make sure that they are still balanced or not. We will see that although 38 and 44 has been affected, but the 3 is still balanced because this is AVL balanced. The height of the left subtree is -1, 0, so the difference here is 1. And this one is balanced as well. The height of the left subtree is 1, the right subtree is 0, the difference is 1. This is AVL balanced as well. Although the height has been updated, but it is still balanced. I still don't do anything. Let me give you another example. Just assume that now I'm going to insert 23 into this tree. If I insert 23, you started from the root. It is smaller than 36, you go to the left. It is greater than 12, you go to the right. It is greater than 17, you go to the right. It is smaller than 27, you go to the left, right? So I have inserted 23 here. Which nodes, the height of which node has been updated? The height of 27 has been updated from 0 to 1. The height of 17 has been updated from 1 to 2. The height of 12 has been updated from 2 to 3. And the height of the root node has been updated as well. It has been updated from 3 to 4, right? So all of these nodes has been affected. But changing in the height is not enough. I have to make sure that I have some nodes imbalanced, right? So the next thing that I need to check is that, so for those nodes that the height of them has been affected, are they still balanced or not? So you will see that 27 is still balanced because the difference between the height of left and right subtree is still 1. How about 17? Is it balanced? 17 is not balanced, right? You can see that here, 17, their height of the left subtree is -1. The height of the right subtree is 1. The difference between these two is 2. And 17 is not balanced anymore. I have to fix the imbalance. Okay, and you will see that this pattern was, do you remember this? This was one of the patterns that we have discussed. Okay, I'm not going to just discuss about how we are fixing this imbalance. I'm still going to talk about where we find the imbalance. Remember, this was the implementation of the insert from the binary search tree. I just got it from the previous lecture, right? This was a recursive definition of the insert. We are going to actually to the left or to the right, right? Starting from the root node, you go to the left, right, until you reach to the to a null reference. You create a node when you reach the null reference, and then all of the function calls are actually going to be returned. So when I am going to check the height of these nodes that has been updated, for example, the height of 27 has been updated, or the height of 17 has been updated, and or this node, and also checking the imbalance, this is exactly here. After you are done with the insert, you need to check that if you have updated the height, and if so, is it still, the node is still balanced or not? Not only this point and this point as well. After you are done with the insertion, when the function call has been coming back, these are exactly the position that you have to check the imbalance. So I need to update my implementation and adding something here that check if T is still balanced. And if in fact what I need, this is exactly what I need to do here as well. So basically here what I need to check is that you will see that if I have inserted something to the left of the tree, just think about it in this way, that you have a tree and this is the full tree, and this is the T is somewhere in the middle from the root until you reach to this point, right? This is T, and you are inserting something to the for example left of T in this subtree. If I have inserted something to the left of T, it is possible that I have increased the height of the left subtree, right? So basically what I need to check here is that if the difference between the height of T dot left minus height of T dot right okay, if it is so far it was actually AVL balanced, right? If it became 2, if it is actually 2, it means that here, right, I got an imbalanced. I exactly need to check something similar to this in this case. If you are inserting something to the right, it means that if I am increasing the height of the right side, height of the T dot right minus, let me just write it as H, height of the T dot left if it became 2, because before that it was balanced, if it became 2, that's it, I found an imbalance. So this is how we are checking imbalance. And then after that I will show you that how we are going to fix it. So basically to check the imbalance, only to check the imbalance, I have to check here and here. After I'm done with the insertion, for example, just assume, look at it, that after I have inserted to the left of 27, after I'm done and coming back, you just check that if the height of the left subtree is greater than the height of the right subtree by 2, the difference is 2, it is imbalanced, I have to fix it. So now you will see that checking the imbalance will depend on the height, right? I need to check the height of the nodes regularly to make sure that if they are balanced or not. So the previous implementation that we had for the binary node or binary trees or binary search trees was that we defined the method height to be a method that applied over the tree, and the time complexity of this method was theta of n, right? We use this recursive definition to calculate the height. But this method is not going to be good for me, because you can see that if I use a method with time complexity of theta of n here to check the height of the nodes, the cost of the method insertion is going to be definitely more than theta of n, right? So we wanted to get theta of log of n. We wanted to make sure that the cost will depend on the log of n. So this additional cost of checking the height is going to be something, inappropriate, and I cannot really waste this much time to calculate the height. How can I fix that? Instead of writing the method height in this way, I'm going to update it. I am going to rewrite the AVL node to make sure that in addition to these three fields, we had it in the binary search tree, right? The element, the item that you store, the left subtree and the right subtree. In addition to this, I'm going to add another field. I'm going to keep the height of the node, each node inside the node. Okay, so we should make sure that when we are updating the tree, the nodes that has been affected, the height is going to be maintained. But when I'm creating a new node, a new node with a single node, the height is going to be 0, right? Later on, I have to make sure that maintain the height. But if I keep the height and make sure that I always maintain the height for all the nodes, now when I am checking the height, instead of writing a recursive method, I can just look at the height of the node. What is t dot height? And that's it. The cost is going to be constant. The cost of this method is going to be constant. And then here, when I'm checking the height of the nodes, the cost for checking the height is going to be constant. Okay, so this was one of the first changes to my binary search tree. Here I defined it as AVL node instead of binary search tree node or binary node. So this is the new class for binary node. I am going to add a field for the height, which is an integer value, basically just tells that for each node, what is the height of that node. So now that we have discussed about the height and fix that issue of calculating the height, let's go back to and check that how we can maintain balance when we are inserting a node or when we are removing a node. What would happen? I'm going to actually go back to our previous example that we have inserted 23 and it caused imbalance for us. Now we wanted to check that how after we find the imbalance, how we can update, how we can fix the imbalance. So remember, we have discussed that all these nodes has been affected, and we wanted to see that which of these nodes are imbalanced. If you look at all these nodes, you will see that node 36 is not balanced anymore, and node 17 is not balanced as well. And the reason is that here the difference between the height of the left subtree and right subtree is 2. And the difference between the height of the left subtree and right subtree here is also 2. The height here is going to be 3. The height here is going to be 1. The difference is 2. So I need to fix imbalance here in 36 and also here. The good thing about the insertion and the nice thing is that if I fix the imbalance at the closest imbalance node that I found, if I fix 17, 36 will be fixed as well. Let me show you. If I fix this node, this was one of the second pattern that we have discussed, right? This is a right-left imbalance. If I'm going to fix this, in fact, this node needs to become the new root, 17 became the left of that, and 27 became the right of that. So this is going to be the fixed form. And you will see that the nice thing about the insertion is that whenever I fix the imbalance in this node, this is AVL balanced, 36 is going to be AVL balanced as well. So I have fixed the imbalance everywhere. This is the nice thing about the insertion. We will see that this is not the case for remove, but let's just focus on this one. So after inserting 23 and we found imbalance, we fixed it, and everything has been actually fixed. Now the tree is going to be balanced. All the nodes in the tree are balanced. Now let's look at another example. Assume that we are going to insert a new node like 6. This node is going to be inserted at, you started from the root, you go to the left, you go to the left, it is smaller than 12, you go to the left, and then you go to the right, it is greater than 3. It is null, you create a node, you put the item, and it is here. Okay, which nodes, the height of which node has been affected? The height of 3 has been affected, right? Because previously it was 0, it has been updated to 1. The height of 7 has been affected because the previous height was 1, now it is 2. The height of 12 has been affected, the previous height was 2, now it is 3. And the height of 36 has been affected as well. It was 3 before and now it is 4. Which nodes are imbalanced? If you think about it, this is, let me use a different color. This is balanced, this is balanced, right? This one is also balanced. The difference between the height of all of the left and right subtree was 1. So all of these are balanced. How about 36? Is it balanced? The height of left subtree is 3. The height of the right subtree is 1. No, this is not balanced. The difference is 2. And this node is not balanced. I have to fix this node. But which pattern is this one? Here I have an imbalance, 36 is not balanced, and I have to fix the imbalance. Can you actually just figure out which pattern is this? If you think about it, you will see that if I think about 36, the imbalance is actually at the left side, right? I have inserted to the left of 36. I have increased the height here. So I have to fix the imbalance on the left side, not on the right side. But which pattern is this one? If you look at the nodes in more deep format, you will see that, okay, in fact, the pattern is left, because that difference actually caused the imbalance is coming from inserting to the left of 36. So here the pattern is left, which tells me that the node 12 should become the new root. And then what would happen to this, all of these subtrees? Or this one? You will see that I'm going to actually just show you that when I have a general pattern like this one, this is a left pattern. But what would happen? You will see that this is not as easy as just, a tree like this one. When you're fixing this, you don't have anything on this subtrees. So it is really easy to take this one and make it the new root. For example, this is 2, this is 1, this is 3. Take the 2 and make it the new 3, and everything is going to be fixed. I'm going to show you that how we are going to generalize this idea to the case like this one. Okay, this is the general case of the first pattern that we have, left imbalance. And this is exactly the same as right as well. Just if you reverse it, it's going to be right. But I'm going to focus on left, just discuss the left. For the right, you just need to reverse everything. Whatever we did on the left, you need to do it on the right, and vice versa. So look at a tree like this. This is exactly similar to what I had here. Before inserting, let me actually kill in here. Before inserting 6, your tree was actually look like this one, right? Just assume that you have a tree like this. This is balanced, right? Just assume that this tree is balanced. This is balanced, this is balanced, and this is balanced. And this is balanced as well, but the difference between the height of left and right subtree is 0. This is balanced. The difference between the height of left and right subtree is 1. Okay, so the tree is balanced, but there is a potential case that it became imbalanced when, if I inserted some item smaller than the value b, okay, if I insert a value like x smaller than b, the value will be, you just assume that you are inserting a value smaller than b. You compare it with f, it is smaller, you go to the left, it is smaller than b, you go to the left, and you will actually insert it in this subtree, right? And it will be inserted as a leaf node here. Just assume that after you are inserting the x, it will actually end up as a leaf node which increase the height of your tree. Okay, something like this one. If you don't increase the height of BL, if you are not increasing the height of BL, so it means that it has been inserted somewhere inside the tree, it's not increasing the height, you are not going to have imbalance. Just assume that you are increasing the height of the subtree, the left of B. This is the case that we are interested in. Otherwise, there is not going to be an imbalance. We have an imbalance if you are increasing the height of BL. So when you are increasing the height of BL, what would happen? The height of left subtree for B is going to be h plus 1. The height of right subtree is h. B is still balanced because the difference is 1. But what about F? F is not balanced anymore. The height of left subtree is going to be h plus 2. The height of right subtree is going to be h. The difference is 2. So I have the imbalance here and I have to fix it. So you can simply assume that there is no imbalance in sub L. All of the nodes in BL should be balanced. Otherwise, if there is any imbalance here, you will fix it here. I'm not going to focus on F. Remember, I told you that we are going to fix the closest imbalanced node. So if there is any imbalance here, I will fix it here. So just assume that everything in BL is balanced and the closest imbalanced node that we have is going to be F. I am going to fix F. This is the first pattern. You will see that this is the first pattern. We call it left-left, right? You can actually just discuss it about right as well. It's going to be exactly the same. Some example of this. This is the first pattern, right? In fact, this is going to be F. This is going to be B. And this is the new node that has been inserted. In that case, BL, the previous BL was in fact empty. This is also the first case. This is F again, this is B, and this is going to be the previous BL. This is again the first imbalanced, right? Because you are inserting to the left of left. This is F, this is B, and this is going the previous BL. So all of these cases are showing that left-left imbalanced. So first, how we can check if the item is imbalanced. This is the check that I need to actually add to my binary search tree. If you look at it, this is exactly here. You have inserted to the left of left. After you are done with the insert, after this line, before the if-else statement here, I'm going to update this side after you are done. In fact, this part, I have it here. This is exactly what I had. You are going to insert to the left of X, the left of T. Here, T is going to be F. Okay, and you have inserted to the left of T, right? You have inserted to the left of t. And then you check that the height of the left subtree, which is b, this is t dot left, right? The height of the left subtree is greater than the height of the right subtree, and the difference is 2. So I'm exactly checking this difference. If it is the case, I have this specific, if it is the case and you are inserting to the left of this one, this is checking that you are inserting to the left of B. So it is in fact telling you that you have inserted to the left of left. Okay, so it is telling me that the pattern that I have, so it is telling me that the pattern that I have is going to be left, left. The difference between the height of left subtree and right subtree is 2, right? And not only that, you are inserting to the left of the, left subtree, you are inserting to the B. Okay, now these 3 dots that I have written for you is what we need to do to fix the imbalance. I'm going to discuss that. What is this one? What we need to do to fix the imbalance. And this part that I discussed, again, I'm emphasizing that this is going to be actually added here. Okay, to fix the left imbalance that we had, remember what I told you? I told you that this is the imbalance, right? What I need to do in this case is that I need to take the middle item, which is B, right, and make it the new root. So B needs to be the new root here. Then what would happen to these subtrees? This one, and this one. It is actually, in this case, it is very easy to figure out that what I'm going to do with this. I'm not going to change this subtree at all because all of these items are going to be greater than F and they are at the right of F. So everything here is good. I'm not going to change the items here as well. This subtree, all of them are smaller than B and they are going to be here and everything here is fixed. I just need to figure out that what I need to do with this one. If B became the new root, I wanted F to be on the right of B, right? Because F is greater than B. So, or I can actually write it as F is greater than B. So I need F to be on the right of B. And all these values are going to be greater than, all of these values are going to be greater than B. But still they are smaller than F, right? So this can be set as the new left of F, right? They are smaller than F and they are greater than B. So what I need to do here is that just assign this one as the new left of F and assign F to be the right of B. This is exactly what I'm going to do, and it will be written as rotate with left child. It's just like you have F, you are at F, right? T is going to be F, and you wanted to rotate T around its left child. This is going to be that method. And I'm going to show you that method here. What I wanted to do in that case is that whatever was the left child of B, I'm going to call it B here, exactly. The F dot left has been stored as B. This is just a temporary variable, right? Then what I need to do here is that to assign the previous right subtree of B to be the new left subtree of F. This is exactly what I'm writing here. Then f dot left is going to become b dot right, the previous right subtree of b. And then I need to update the right children of b is going to be f. So these are exactly the two actions that I need to do. Update the left subtree of b and update the right subtree of b. Okay, after I'm done, you will see that the new root of this subtree is not f anymore. The new root, the previous root was f. I am changing it to b. So you can see that what I'm returning at the end is going to be b. This rotate with left child, this is the method that I'm calling here. Okay, so you pass t, which was f, and whatever will be returned should be in fact b. So t will be updated to be in fact this node. The root is going to be b. Before I leave the this method, I just need to make sure that the height of the nodes has been updated as well. You can see that by changing f to become the child of b, the height of f and b will be affected, right? So I'm going to update the height of f and update the height of b as well. The height of the other nodes are not going to be updated. They are not going to change. Only you have updated this one and this one, right? You change the order of these two. B was the child of f and now it is the parent of f. So I need to update the height of f first, and then after that I need to update the height of b. And what is going to be the height? I'm going to actually just use that recursive definition. Whatever is the height of the left subtree, right subtree, give the maximum between these two plus 1. And also for the b, I can just check that whatever is the height of the left subtree and the height of the right subtree, instead of actually writing it at b dot right, I just wrote it as f dot right to f dot height to actually tell you that, yeah, the right subtree of b is f, in fact. So the height of the f and b has been updated, and then you return the reference b. And we are done. This was as simple as this. Now you can actually, if you think about the time complexity of this fixing this pattern, you will see that the time complexity is in fact constant, right? Because here I'm just changing a couple of references. This method, this updating the height is constant, this updating the height is constant, and you just return the reference. The total time complexity for updating the height, for fixing the imbalance is going to be constant. And I have actually put all of that here. We checked for the imbalance. If we found the left imbalance, if this was true and this was also true, it means that I have a left imbalance. So I need to rotate with left child and I will fix it here. And that's it. This was the first case. If you think about in the larger scale, after we have fixed the imbalance, that left imbalance, tree is going to look like this. So the previous tree was this one. We inserted a new node. After the insertion, we had imbalance, then fixed the imbalance, and now you can see that, okay, everything in the tree is going to be balanced again. And not only that, the height of the previous tree before insertion was h plus 2. The height of this part of the tree after the fixing the imbalance is still h plus 2. So everything else, all the other nodes on top of the b, are not going to be updated anymore because the height of them hasn't been changed because we fixed the imbalance here and everything is in place. So let me show you the original example that we had. Remember, we inserted 6 to this tree and we figured out that this pattern is left left. You have inserted to the left of 36, which caused the imbalance for 36. If we are going to fix that, the new root node should be 12. 12 should be the new root node. This part is going to be assigned as the left of 36, and 36 will be assigned as the right side of the 12. So this is going to be the new tree after fixing imbalance. More examples here. Remember, it was all different cases of the left imbalance. In all of these cases, the 17 was F, according to F. This was B, and B should be the new root. You will see that in all of these cases, B is actually becoming the new root. In all of the cases, we have left imbalance, and B became the new root. This subtree became the left of F, and F became the right of B.